Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be working through the June 2015 Unit 1 Paper 2, and we'll be working on question 2, which was a question based on redox equilibria. So first, we have to define each of the following terms. And the first term is standard electrode potential of a half cell. Now, the standard electrode potential of a half cell refers to the voltage measured under standard conditions with the standard hydrogen electrode as the other half cell. Okay? The other term that we have to define is the standard cell potential of an electrochemical cell. So now we have a whole cell that they're asking us about. And the standard cell potential of an electrochemical cell refers to the voltage that's developed under standard conditions when two standard half cells are joined, right? So that's a whole cell now. When we join two half cells under standard conditions, that's what the standard cell potential refers to, the voltage that's developed in that condition. Okay? All right, so moving right along. Part B says, consider the following unbalanced equation, which describes the process that is taking place in an electrochemical cell under standard conditions. So we have an electrochemical cell, and this is what's going on inside of that cell. We have 1 mole of aluminum solid reacting with 1 mole of tin ions in the 2+ state in the aqueous phase, and that's then being converted to Al3+ in the aqueous phase, and then we got our 1 mole of tin in the solid phase, right? So that's the reaction that's taking place in the electrochemical cell at standard conditions. So the first question says, write the ionic half equation for the reaction taking place at each of the electrodes, right? So at each of the electrodes, we have, let's start with the anode, right? So we know that at the anode, it's where oxidation is taking place. And so when we look at our full equation, we see that the species or the metal that's being oxidized is the aluminum, right? Because it goes from, let me just put some numbers here. The aluminum in the solid state has an oxidation state of 0. And then over here, it ends up being 3+. Right? So we're going from 0 to 3+, so that's an oxidation of the aluminum metal. And so when we think about what will be happening at our anode, it has to be we have to be showing that there's an oxidation process there, and that is this aluminum that's getting oxidized, okay? And oxidation is a loss of electrons, and so we have the 3 electrons that the aluminum metal would have lost in order to become Al3+. So we have that shown here as well, okay? All right, so that's what's happening at our anode. Now at our cathode, right? At our cathode, what's going on? Reduction, right? We know that we're gonna have to show a reduction process taking place at our cathode. When we look at the full reaction, we see that we have our tin in the 2+ state that ends up at just tin metal in its, just pure metal state. And so we have a reduction of that oxidation number, right? The tin is going from 2+ to 0. And so that's exactly what we have to capture in this half reaction. Now make note of the fact that because we're showing a reduction, and reduction is a gain of electrons, we're going to show the Sn2+ ion as gaining those 2 electrons, and then finally resulting in the formation of that tin with the 0 oxidation state, a pure metal. So there's a reduction in the oxidation number from 2+ to 0. And so that's what's going on at our cathode, okay? So those are our 2 halves that make this whole, okay? All right. So moving right along, we're now being asked to write the cell diagram, right? Now, when we're writing a cell diagram, what we're gonna have is just like a one-liner that describes exactly what's going on in the electrochemical cell. And so here's that one-liner. Our one-liner is constructed to show our anode portion on the left. So that whatever we just wrote on the left that's going on in the anode, up here, we're going to write in the left. So I write my AL, and I have this line here, that straight up vertical line that represents a phase change, right? So it's showing me that I'm going from Al in the solid phase to Al3 plus in the aqueous phase. And that's what's going on in my anode, right? Then we're going to have this two lines, right? Two vertical lines represents a salt bridge. That's going to connect both halves. And so now on this half is my cathode half. On the right-hand side, we're going to show our cathode half of that electrochemical cell. And as we said in our cathode half, we're going to show the SN2 plus in the aqueous phase being reduced, right, to the tin in the solid phase. So this should be a single line again that represents a phase change, right? So just a single line there that represents a phase change as we're going from SN2 plus to SN solid, okay? So a single line. The only time we're gonna have a double line is when we're showing the salt bridge in our cell diagram, okay? And so this is the cell diagram that was required of us. It's literally just a one-liner that summarizes the whole reaction that's going on in the half cell, okay? Anode to the left, cathode to the right, salt bridge in the middle, okay? All right, so moving right along, what we're gonna do now is we're being asked to draw a well-labeled diagram of the electrochemical cell, and we need to indicate the direction of electron flow, okay? So I'm gonna bring up my cell diagram again that we just drew, and I'm gonna again make sure that I correct this one to show you that in the cell diagram, it's only a single vertical line that should be here, and that one is the one that represents a phase change, right? We just discussed this on the previous question that this should be just a single line here. Okay, so whenever I'm asked to draw my cell, a well-labeled cell diagram, if I have a well-labeled electrochemical cell, if I already have my cell diagram, all I have to do is just put that in a circuit form, right? And so I'm gonna start by drawing my anode portion first, okay? So I'm gonna draw my anode portion first. And here's my anode. I'm gonna draw my anode to the left, right? I'm just gonna keep that convention going where we draw the anode towards the left, and then on the right would be our cathode. Just as how we have it in the cell diagram, that's how we're gonna draw the actual cell. So I'm gonna put my cathode over here. I'm gonna put my cathode in a different color. Let's use white for the cathode, actually. So I'm gonna put my cathode over here. So this is my beaker, right? That's my beaker in which I will have my solution of my ions. And then over here as well, I'll have the same thing, a solution of my ions there. Okay. So let's complete this out now. So because this is my anode, I'm gonna have a sheet, like a metal sheet. And that metal sheet is gonna be made up of what? That's my aluminum in the solid phase, right? So that's my Al solid. That's what my anode will be made up of, Al solid. And that sheet of Al solid is going to be placed into a solution that contains Al3 plus ions in the aqueous phase, okay? And so that represents my anode. A similar thing is happening at my cathode, except my cathode is going to be made up of tin, a metal sheet of tin, right? So that's SN solid. And that metal sheet of tin is going to be placed into an aqueous solution containing tin ions, okay? So that's that connection there. And so that's where that equilibrium gets set up for the tin. Let's write that. So in this particular case, remember, this is our cathode, and that's where reduction takes place. So I'm going to write it as such, that I have my SN2 plus aqueous plus 2e, so it's gaining 2 moles of electrons, and equilibrium gets set up, and then that's how my SN solid is formed. And then over here at my anode, where oxidation is taking place, my Al solid sheet is then getting oxidized to Al3 plus. And in so doing, it has lost 3 electrons to have gotten to that point. Okay? So that's my reaction at my anode. So let's just write anode over here. That's an oxidation process. And at this is gonna be my cathode, and where my reduction is taking place. Okay, so now I have to connect the 2 half cells. And so there's a wire that connects them both up here. And that wire is gonna have a voltmeter in the middle that I'm gonna be able to read off those voltages from. That would be my standard cell potential, guys, of this electrochemical cell that I'll read here, right? And then I also have a salt bridge, which is represented by those 2 double line there. So I'm gonna put my salt bridge in, which color? Orange. I'm gonna just put my salt bridge here, and my salt bridge actually goes down into the solution as well. It touches the solution, okay? So this is my salt bridge in orange. Okay, so let me just label that. That's my salt bridge. No, the question didn't specifically tell us what the salt bridge is made up of, but we know there has to be a salt bridge, and generally it can be made up of any strong electrolyte, right? So it can be made up of KNO3 or KCl, or it can be made up of NaCl, any strong ionic compound, right? Can be used to make the salt bridge, and it will just send ions to the respective cells as needed to maintain a charge balance, okay? All right, so we have our salt bridge, we have our wire through which the electrons are gonna flow, we have our voltmeter, which from where we'll be able to get our standard cell potential reading, okay? So here we are now. We're asked to indicate the direction of electron flow. Okay, so let's think about this very critically. The anode, right, in the anode half cell, right, that's where electrons are lost. Do you see that? Oxidation is lost, and so here's the electrons that are lost. If the electrons are lost here, then that means that they're gonna come up out of here, okay? They're gonna come up out of here, that's where they're lost, and then they're gonna travel through the wire, and then they're gonna come down. They're gonna come down now and enter my cathode. At my cathode is where reduction takes place. So my SN2 plus that's in the solution can latch on to these electrons, and then it gets reduced to tin solid. Okay, so that's the process that's going on here. My electron flow is always gonna be from anode. So let's write that the direction of electron flow is always gonna be from my anode to my cathode. Okay? All right. And so with that, we've completed this part of the question where we're drawing the well-labeled diagram of the electrochemical cell. Okay, so our voltmeter reading will be here. And as I said, that voltmeter reading, let me just make it very clear at this point that that voltmeter reading, whatever that voltmeter reads, that's what we're gonna call our standard cell potential. Cell potential. And for short, you may see it written as E standard cell. Okay, so that whatever the voltmeter reads, that's the standard cell potential because we've connected 2 half cells under standard conditions, okay? All right, so we're ready to move on to part C of this question now. So let's move on, or to the final part rather. So let's clear this and we're gonna move on. So here's the final part. So this is part 4. Okay, so part 4 says for each electrode shown in the table below, select the theta value or the electrode potential value to determine the standard cell potential value. So we're using standard electrode potentials to find the standard cell potential. Okay, so this was the reaction that we were working with, right? We've been working with for this entire question. And as I said, single line, phase change. Hopefully you guys never forget that. A single upright line is for phase change. The only double line is for our salt bridge, and that should be here. So I corrected that again. All right. So we're going to calculate the E theta for the cell. The standard cell potential is what we need to calculate. So what was our species again? At our anode, we had this guy. We had the aluminum. So we're going to look for this one. So this one here, let me just box it. Let me use a box to circle that one. So this was our anode. Yeah, this was our anode. So I'm going to need to use that. Right, I'm going to need to use that standard electrode potential for my anode. So I'm going to just box that one. We're going to need to use that for anode, right? And then for the cathode portion, it was what? It was the SN2 plus that was going to SN solid. So that was a reduction process. So I'm going to need to use, I'm just going to box that in. Let's put that one in pink. So this is the one, okay? This is the one because it was the reduction of SN2 plus to SN. So we're going to select that one for our cathode. So let's just write that there, that this box would represent the standard electrode potential of our cathode, okay? All right. So here is what we're going to need to do now. Whenever we're finding this guy, so whenever we're finding E theta cell, which is our standard cell potential, that's going to be equal to the standard electrode potential at my cathode. And then from that, I'm going to minus, right, the standard cell potential at my anode, right? So all I have to do is plug in the numbers there. So the standard cell potential at my cathode was this guy. So I'm just going to drop that number here, 0.14. And then I'm going to minus off whatever it was on my anode, which was minus 1.66. Okay. And when I do that, effectively, what I end up doing is I end up adding my standard electrode potential at the cathode to this guy. Okay. And so with that, we come out with a value of positive 1.52 volts. And so that's what the voltmeter that we had previously drawn in our well-labeled cell diagram, that's what that voltmeter would read. Okay. So when I connect these two half cells, right, this being my anode and this being my cathode, the voltmeter will read 1.52 volts. And so that's my standard cell potential. And that's how we go about calculating it. Okay. And so with that, we've come to the end of this question. Consider subscribing to the channel. And if you look here, right, on your left, you will see the next video up. If you look on your right, you will see the Module 2 playlist, where there are tons of other content for you to indulge in and get yourself ready for this exam, okay? Thanks for watching and see you in our next video.